Right, right. All right, so let's talk about deletion from binary trees. So this is, as I've said, I never talked about PA3 in here, did I? Because we didn't meet on Monday. So PA3 got graded and turned in. PA3 was a good job. No issues or concerns that I saw for the most part on what people did. So stacks and queues, people got them working. Good coding styles as usual, good commenting in most cases. And the code tended to work pretty much the way it was supposed to. The biggest issue I saw some people run into for PA3 was dealing with the tail pointer. And because of the way we were doing the tail pointer, there's two cases that you need to deal with when you're adding to a queue. So remember, our queue setup was like, here was our sentinel, here was our first data, here was our second data, and so on. And our sentinel had a tail pointer pointing to the last node. So in general, when you want to add something to the queue, you create a new node. You find the last node by following the tail pointer. You set that last node's next to point to your new node, and then you change the tail pointer to point to your new node. But if your list is empty, it's usually an edge case, because when you want to add something to an empty queue, we can't really follow the tail pointer to find what the previous node is, because there is no last node in this list, right? Unless maybe you set tail pointer for an empty list to point to the sentinel. But in general, the easiest thing to do is just make two cases. Case one, if the sentinel's next field is null, you know you have an empty list. So make a new node, have the sentinel point to that node, and have the tail pointer point to that. Case two, the sentinel's next field is not null. In that case, make a new node, follow the tail pointer to find your last node, set that thing's next field to point to your new node, and then set the tail pointer to point to your new node. But they're two fundamentally different sets of code. And what I found in some cases, if I told you that your queue stopped working at some point, what I was doing was I was putting things into your queue and then deleting things from your queue until it was empty, and then deleting a few more times and getting your error saying the queue was empty, and then trying to insert into the queue, and it was not putting anything in. But in, I think, every single case where this happened, I was getting Valgrind to complain to me. So if I ran your code with Valgrind and I deleted a bunch of things and then I tried to insert something into an empty queue, I would usually get a bunch of messages from Valgrind, warning messages. And after that, subsequent inserts into the queue didn't work. And if you trace it down, so this is where you make yourself a small test case that causes this Valgrind complaint, and then run this through GDB without Valgrind, do the same test case, but look at what your code's doing. And usually what you'll find is that once you've removed everything from your queue, your tail pointer is pointing to what used to be the last node in your queue. And when you try to add a new node, you're trying to take this thing, which has been freed, and have it point to your new node. And Valgrind's complaining that you're using a block that's already been freed. So that popped up in some cases, and it's just another one of those edge cases. And we start bumping into more and more edge cases throughout the course from this point forward. But other than that, stacks and queues seemed to work great. So I was really happy with what I saw. Good coding styles, like I said. No issues. A few people forgot to put their names in their code, so don't forget to put your names in. And yeah, so I thought PA3 was really good. So definitely come and talk to me if there were anything in the comments I made and such that weren't clear. All right, so now let's look at deletion from a tree. So just like insert, we potentially change the root of a tree when we delete from it. So we've got to return a tree node pointer. So we'll pass in the root, and we'll pass in the number we're trying to delete. And for simplicity, let's say that our number must be in the tree. So you've called search first to make sure this number is in the tree. Otherwise, give the user a message saying you can't delete that, it's not in the tree. So we're assuming our number is in the tree. And let's suppose we want to delete the root of the tree, because the root's equal to our number. All right, so let's suppose this is our tree, and we're trying to delete the 20. So our general algorithm was go into the left subtree, find the largest number in there. That's the 15. And we're going to make 15 the new root of the tree. We're getting rid of the old root. 15 is going to be the new root. Okay, and we're not copying data values. We're not just changing this 20 to a 15. We're getting rid of the 20. We're taking the 15 and we're actually putting it in place as the new root. So what do we need to do? Find the largest node in left subtree. So do the thing that you're doing in ODP, whatever number we're up to, 215 maybe. Do the thing that we just talked about. Go down to the left, march down to the right until you find the largest node. And I'm just going to assume that's a node pointer called largest. Okay, so in this case, this is largest. Is that 15 right there? Okay, what does it mean to make that the root? It means that largest left should take on whatever root had on the left, and largest right should take on whatever root had on the right. So this 15 is going to pick up a 10 on the left and pick up a 40 on the right. That's going to basically make it the root of the tree. And the 15 doesn't have anything to its right to begin with, because it's the largest node in this subtree. And if it had something on the right, that something would be bigger than 15, because that's how binary search trees work. So we know 15 has nothing on the right. There's no harm in saying 15 right equals all of this stuff. But 15 could have things on its left. And if we just say largest left equals root left, we've orphaned this entire subtree. But since we know that 15 is a right child of 10, when we move 15, 10's right child is going to be free. So if we can remember what this previous node was, we can say previous right equals largest left. So here's the action. Previous right is going to adopt 15's left child. And 15 is basically going to come up here to the root, so its left child will be root's left, and its right child will be root's right. And then we're going to free the root. Which is going to release this and send it back into the heap. And so there's our tree after we've deleted the 20. 15's now the root. On the left, it has everything that used to be on the root of 20. And on the right, it has everything that used to be on the right of 20. And where we used to have that 15, right, its left children have been adopted by 15's parent. and 15 was the right child of its parent, so its parent adopted on its right all of 15's left children. So that's the algorithm, right? Find the largest thing, make it the root, have the parent adopt all of that largest node's left children. There's some statements that do something like that, but this needs some clarification. Finding the largest node in the left subtree, calling it largest, but also keeping track of the previous node. So how can we do that? So something like current equals root arrow left. So that gets us into our initial left subtree, which would be this 10. And then while current right is not null, let's set previous equal to current and current equal to current right. So let's see what this does. 20, 10, 15, 13, 14, 12, 11, and some other stuff over there on the right. All right, so current, so here's the root. Current will be root arrow left. And while current right is not null, we'll set previous equal to current, and we'll set current equal to current arrow right, and we'll come back up. While current right is not null, while current right is null, so we exit our while loop, and now we've got previous pointing to this, and current, which we were calling largest a minute ago for some reason. Current's the largest node in our subtree. And so we can set previous right equal to current left equals root left, current right equals root right. So this was largest. So we're doing the linked list thing. We're keeping track of the node we're at, but also the prior node. But we've still got some edge cases here. So one edge case is what if our tree looks like this? What if the largest node in the left subtree is the root of the left subtree? This code's not going to work, because this is going to say, here's our root, here's our current, and we're going to say, well, current right is not null, but the first time we look at this condition, current right is null, we're going to exit from our loop. And so we know what our node is, but we don't know who should adopt our current's left children. We don't have a previous node. And this is not a valid previous node because this node's going away. So this is a different case. If our tree looks like this, so let's start off with current equals root left. If current right is null, then we can't do this loop up here. In fact, what we want to do is simply take this entire tree and adopt the root's right child on the right. In other words, we're not going to orphan the left child of our largest node. So in this case, we're just going to say current right equals root right. Free the root and return current. So this thing adopts all of that. We get rid of the root and we just return that largest node as the new root of the tree. Want to see that part again? Did I take it away too soon? Good? All right. Right, so if this is what our tree looks like, I snuck some fractions in there on you. This is what our tree looks like, and we're deleting the 20. We're going to put the largest thing in our right subtree, which is a 14, up at the root. That's going to have all the stuff that used to be on the left. There's the 12 over there. But instead of having a 14, which we removed, it's going to adopt the 13, the 12 and a half, 13 and a half, and so on. And the right side's going to be the same. But our exceptional case starts off with this. And to delete the 20, we're just going to make 10 our root and adopt whatever was on the right side of the root. So you need at least two pieces of code. One to handle the case where the left subtree doesn't have anything on the right, and one where it does have something on the right, and you can march down and find it. But we've got another edge case. Which is where there is no left subtree at all. And all of this code assumes that we can somehow get to the left subtree of the root and do some analysis on it. Well, we have an extra case. If root left is null, then we can't look for the largest node in the left subtree because there is no left subtree. So in this case, our deletion algorithm is different. All we do is simply get rid of the 20 and change the root to be the right child of 20. So we can do something like temp equals root, arrow right, free the root, and return temp. All right, so let's put this together. So if the root data is equal to the number we're trying to delete, check to see if the left subtree is null. If it is, move the root to the right subtree. That's the last case we just looked at. And return. If root left has no right subtree, right, that's the case where we have a left subtree, but there's nothing to the right of that subtree. And in that case, we simply make this node's right subtree equal to the root's right subtree. So So move root left to root and adopt the old root's right subtree. And return the new root as usual. Otherwise, we've got this case where we have a left subtree and we have at least one thing to the right. So else iterate, find previous and largest, and so on and so forth. So do that first algorithm that we talked about, which was this one. And free the root and return the new root. And that's all just for deleting the root of the tree. But what if we want to delete something that's not at the root of the tree? What if our number that we're trying to delete is less than the root data? Well, this is where we can recurse. So if our number is smaller than the root data, it must be found in the left subtree. So let's just delete from the left subtree our number, and then set root's left subtree equal to that modified tree, and return the root. Otherwise, our number is not equal to the root, it's not less than the root, it must be greater than the root. So set the right subtree equal to what we get when we delete our number from the right subtree. And then return the root. So there's a more or less complete deletion algorithm with several lines of code in place of each thing we've written up there in the first half. So lots of steps here, right? So how do you write this? You want to be really good at making trees. So you either want an insert routine that you absolutely trust, or you want to cobble together trees by just making nodes and setting what the things point to and so on and so forth. So you want a way to create trees, and then you want to play around with deleting the root. And you want to try different cases. Try deleting from a tree where you've got something on the left and something on the right. Try deleting from a tree where you have nothing on the left or the right, or just stuff on the left. Or you've got a subtree on the left with no right subtree, or you've got a subtree on the left with a right subtree. And it's not clear what's going to be the trickiest case here. But here's one tree to try to delete the root of. Here's another one. Here's another one. Here's another. Here's another. And I think each of these exercise different pieces of your algorithm. Maybe not these so much, but certainly this, and this. Different edge cases. This is your most general, right? Maybe do one more. See if you can come down at least a few hops from the left subtree's root. And if it works on these, it's probably working. Right? Once you're positive, or pretty positive, that it's deleting the root successfully, then go ahead and add the recursive steps. And then you should be able to take a tree and delete any node from it. And you can try deleting leaf nodes, you can try deleting things in the middle, you can still delete the root. and so on. And the first few times you try this, it probably won't work unless you're really lucky and good. But chances are, the first few times it'll loop forever, or it'll segfault, or it'll corrupt your tree in some way, right? So you want to be developing these cases as you're testing them, because you don't want 100 lines of delete code that just blows up, right? So work on subcases and keep adding edge cases and get to the more general, or the other way around. And as you put more and more test cases into it and it's working better and better, right, eventually you get to a point where you can delete from a tree in general. Then you go ahead and you make yourself a huge tree and you just delete nodes at random and make sure that it's doing the right thing. And test that as many different ways as you can. So 50 different deletion tests is probably not unheard of when you're doing this. Dozens, I don't know. But you definitely want to exercise the heck out of this, because there's lots of ways where it can look like it's working right, but you never actually tested this case where the largest node was exactly the right child of the left subtree's root. And that might be an edge case depending on how you write your code. So get very aggressive with it as it looks more and more like it's doing the right thing. Keep hitting it with lots of different test cases. Swap with friends, right? Don't share source code, but if you want to exercise each other's code, see if you can break it, right? Make a bet out of it or something. All right, so that's pretty much deletion at a high level view. Tree traversal we've talked about. We went through queue-based breadth-first traversal last week. Depth-first traversal, do recursively. Queue-based, you do iteratively. Okay, that doesn't recurse easily. Depth-first is inherently recursive. How do you do an in-order traversal? Do an in-order traversal on the left, print the root data, do an in-order traversal on the right. Right, it's nothing to it if you do it recursively. The height function we talked about, right? So it's 1 plus the largest height of the left subtree or the right subtree. And if the tree is null, you just return -1. And balance is a recursive definition. It's balanced if the heights are within 1 and the left and right subtrees are balanced. And I think that's all you need for your functions. So you can push delete off for later. Get your insert working, search, traversals, and then come back and start looping on delete. Questions? All right. I told the other class PA4 is probably about 10 times harder than PA3. There's just a lot more code. It's hairier to debug and to sort of trace what's going on and so on. So if you haven't already started working on it pretty seriously, you definitely want to soon, because it takes a long time. It's probably not doable in one setting. And it's probably going to take some long sessions. All right, let's switch gears and talk about tries. Tries are one of my favorite data structures for a variety of reasons. They're really powerful, they're really efficient, and they're just weird, which is always kind of cool to me. So what's the idea of a try? It's an n-way tree. Binary trees are two-way trees. You have a left child and a right child. A try will typically have dozens of children from each node. And we can use a try, for example, to store words. So let's say we wanted to store words or phrases, combinations of characters, in a structure that lets us efficiently store them and efficiently retrieve them, do searches for words in our structure. Now we can store words in a binary tree, right? We can order them by using string compare. and words that come before the root go on the left, words that come after the root go on the right, and we can do it exactly like we do a binary search tree. The problem with a binary search tree, it's log base 2 of n levels to a balanced tree. And the height of the tree, the number of levels, tells you how long it takes to find something or to insert something. So if you have a billion nodes, it takes you 30 operations to move down from the root to a leaf, assuming it's well balanced. 2 to the 30th is a billion. And you have to keep them balanced, which is a whole nother story. So what does the trie look like? Well, here's a typical node. And each node corresponds to a letter of the alphabet. So we're going to have 26 nodes, one for each letter. We're just assuming uppercase letters, no punctuation. So 26 characters. And then we have one more field, which we call EOW, which means end of word. All right, so how do we store information in our trie? We start off, our trie is empty, so the root is null. So let's say we want to store the word cat. Okay, we create an initial node, and all of these pointers are null. There's no children on this, except for the node corresponding to C. So for this field in our first node, we're going to store the address of another node. So these are all null. And end of word is a 0. But this is going to point to another node. And the A field is going to point to another node. And all of these are going to be null. And end of word will be 0. And on this node, all of these fields are going to be null, except for the pointer corresponding to T, and that's going to point to another node where all of these are null, and the end of word is equal to 1. Okay, so what does this represent? We start with our first node. If there's a field which is not null, it means that there's a word starting with that letter. So C is, this third field is not null, so we have a word stored in our structure that starts with the letter C. And that points to another node where there's a non-null entry for the first field, which corresponds to the letter A. So there's a word starting with CA, and that points to another node where T is non-empty, so there's a word starting with CAT. And that points to a node where the end of word value is 1. That means CAT is part of our structure. So in this data structure, we have one word stored, which is the word cat. Now let's store the word cab. So we go over to the C, that points to another node. We look at the A field, that's not null, so that points to another node. But now the B field, instead of being null, is going to point to another node. And the end of word field of that is going to be set to 1. So we can go C-A-T, end of word, that's cat, or we can go C-A-B, end of word, that's cab. So we've got two words stored in our structure now. So let's put a dog in. So D, instead of being null, is going to point to a node. And the O entry is going to point to another node. And the G entry is going to point to another node. And that node's going to have an end of word field of 1. And And so we've got a DOG in our try. All right, let's store cats. So we've got C, that points to a node. We've got A, that points to another node. We've got T, that points to another node. In this node, the S field is going to point to another node. And that's going to have an end of word equal to 1. So we start off with C, A, T. And since that points to something with an end of word equal to 1, we know that CAT is part of the try. But we can also see that the S points somewhere, and that points down to another node with an end of word equal to 1. So cats is a part of our try also. Is this making sense? So it's unambiguously letting us store words in this collection of nodes. The cool thing is the number of operations you have to do to find if a word is in your try is bound by the number of letters in your word. So if I know that no word has more than 11 letters, I can find any word in this structure in 11 operations, no matter how many words I have stored in here. And there's 26 to the 11th possible words. That's a lot of words. Doesn't matter, 11 operations, I can find or either conclude that any word is not found in this structure. So this is order 1, right? This is a fixed amount of time, regardless of how much data we store in this. And that's pretty cool. But it's a memory hog, right? We've got all these big nodes that have 26 pointers plus a flag. And for every letter and every set of letters that are unique up to that point, we have that many nodes in this structure. So this consumes a lot of memory, but it's very time efficient. And it's just plain fun to code. So your node structure is a bunch of pointers. And an end of word flag. But it's probably not really practical to have 26 different field names, A, B, C, D, up through Z, right? So you would probably make an array of these things. So struct try node next bracket 26. So now we have an array of next fields inside each node, as well as a flag. And so how do you store something? Well, you take your string that you're trying to store, you look at your first character, so string bracket 0. You look at your root node, and you check next bracket, whatever index corresponds to that character. And if it's null, then you have to create a new node, point that indexed pointer to that new node, and continue. If it's not null, you simply follow it and work with your second letter and keep doing this until you get to the end of your word, and then you take that last letter. And if that's pointing to a node, you simply go to that node, set the end of word to 1. If it's not pointing to a node, you make one more node, point to it, set the end of word to 1. If it points to a node that already has end of word set to 1, you're trying to insert something that's already in your try. And your search is just a subset of those operations, which is to just go through letter by letter from your word and follow these. If you get to a point where your letter is pointing to null, you know your word's not found in the try. When you get to the last letter, if that's pointing to a node, see if that node has end of word set. If it does, your word's in the try. If not, then it's not. You're looking for cat, and you've got cats with an S at the end, but you don't have cat. So does that make sense? I don't know. I've never coded one of these recursively. I think you could. Yeah, so if you've got cat, you could go down to the C, either follow the node or create a node, and then say insert at, using that as the root. That should work. That would be pretty cool. So let's take a minute, reflect on this. Space is the amount of memory, the amount of resources that we need to do something. Time is the amount of time it takes. And we've already seen that an array, which is pretty space efficient, it's really just, if you have an array of integers, it's 4 bytes per integer, right? So it takes very little space, but for a lot of operations, pretty inefficient. If we move to a linked list, we need more space because now we have these nodes for each piece of data, but some of our operations become more efficient, and so we move over, take more space, take a little less time. If we go to a binary tree, we need even more space because now we have even more complex nodes, possibly with parent pointers and so on, but a lot more efficient in time. If we go all the way out to a trie, our time comes down to pretty much 1. It's a fixed amount of operations, but our space gets really huge. And you can start looking at algorithms and you can kind of see some sort of general trends here where we can kind of trade off space for time. And this is a recurring theme in computer science and engineering. If you want to add a bunch of numbers together, let's say you want to add two 64-bit numbers, we could take what we do with pencil and paper, add these two numbers together, carry it over, get that sum, carry that over, get this sum. 64 operations later, we would be done. We'd have our sum. And the only amount of hardware that we need is the hardware of a 1-bit adder. But we could design a 4-bit adder and add our numbers 4 bits at a time and do that 16 times. It takes 1/4 as much time, but the hardware for doing a 4-bit adder is much larger than a 1-bit adder. So it's going to take more space, less time. We could make a hardware 64-bit adder. You get 64 XOR gates and probably about 30 breadboards, right? And you could build something that at the hardware level implements the truth table for a 64-bit adder. It's going to be very efficient, but a horrible amount of space. And a lot of problems can be solved by sort of choosing where we want to sit on the space-time curve. Right? This is like cracking passwords. If you have software, you can just try each password one after another until you find the one that gets you in. It takes a long time, not a lot of hardware. You can run it on a Raspberry Pi. If you had 4 billion Raspberry Pis, you could try 4 billion passwords like that. Each one tries a different password. And whichever one gets in turns on an LED and displays what the correct password is. And a lot of algorithms work like this. We can either take a lot of time with a little space, a little memory, a little hardware, or we can take a lot of hardware and less time. But, you know, ideally, we'd like to find something down here. It takes very little time, very little space. That's hard to do. What we don't want is something up here that takes a lot of time and a lot of space. That's easy to do. That's usually a bad algorithm. But we seem to ride this curve a lot. So this is where a lot of my research has gone over the past 30-some years, is looking at moving towards this space-intensive, time-efficient. area of computation. So that's where you get into things like nano-inspired architectures and so-called Avogadro machines where you have, say, 10 to the 24th processors, and you just throw problems at it and it just spits back answers right away. So that's one possible direction for the future. All right, we can end on that. That's a lot of material, so don't panic if it's confusing right now, because we went through a lot of stuff, right? So the main point is tree algorithms, right? The secondary main point is deletions, in particular from trees, and then tries are just kind of on there as icing, and we might touch back on them later. All right, have a good rest of the week, and stay safe weather-wise, and I will see you next time.